Hi, everybody. Welcome back. In this video, we're going to take a little bit of a break from discussing the biology and the specifics of how we model biological and biochemical systems in particular, and define a little bit of the fundamental ideas in probability theory that are going to be important for the discussion in the next couple of lectures. For some of you, this might be a bit of a review if you've taken probability before. For others, it might be new. We're not going to be digging into this very deeply. The point here is really to define some of the key ideas, terms, and notation so that you can follow along with the discussion in the next couple of lectures. So let me begin with switching over to the slides, and we'll move forward from there. So the first idea I would like to define, this is a very, very important concept in probability, is the idea of a random variable. A random variable fundamentally is a numerical representation of some event that can occur, that occurs subject to random chance. This may be true random chance, like the, say, decay of a nucleus in an atom, or something effectively random, the arrival time of a bus in the city, for example, that has enough confounding factors that we don't know enough about, and that all sort of interact with one another in complex ways, so that the arrival time, at least measured down to sort of minutes or seconds, is fairly random. You can also even think of traditional random events like the roll of a die fundamentally have some physics underlying the outcome in sort of how the die bounces around inside the cup or inside a person's hands, but the physics of that process is so sensitive to specific angles and builds up on so many iterative interactions that the value is as random as you can really get. So things like the value of a rolled die, the result of a coin toss, and so on are random events. We can represent their outcome with a random variable. We use a random variable to describe, in general terms, the outcome that could occur. When we take a given experiment or a given observation, we actually roll that die instead of just thinking about rolling the die. Then the random variable takes on a unique value. That is a specific value that is unique to that experiment. A subsequent experiment might take on the same value, or it might take on a different value. The likelihood of a random variable taking on a specific value is described by a probability distribution. We'll talk a little bit more about these in a minute. And by convention, we use uppercase letters to denote a random variable, and lowercase letters to denote a specific value taken on by a random variable. These conventions are usually followed or often followed. There are always exceptions to convention. All right. So let's maybe go through a little bit of an example to give you a feeling for the sort of notation we use. Okay? So by convention, we use uppercase letters to denote a random variable, numbers or lowercase variables to denote a specific value taken on by a random variable. And we often may wish to describe the set of all possible random variables, all possible values taken on by a random variable, by S, with a subscript of that random variable. So let's think about an example. let X be a random variable describing the roll of one 6-sided die. Of course, the set of possible outcomes is S sub X, 1, 2, 3, 4, 5, or 6, the possible outcomes of rolling a die. We describe the probabilities that that variable takes on specific values using probability distributions. The probability of rolling each number, and how would we write this? The probability that the random variable X takes on value X is 1/6 for all X in this set. This is just the notation for saying we have a 1 in 6 chance of rolling every number. Every number is equal. The probability of rolling a 3 or less, the probability that random variable X takes on a value less than or equal to 3. This, of course, is half. Half of the possible outcomes are 3 or less. The probability of not rolling a 1, we might say the probability that random variable X does not take on the value 1 is 5/6. There's 5 choices that are not a 1 out of 6 total choices. This should give you a feel for the notation in a system where the probabilities are easy to understand. The underlying process is a simple one. Now, let's talk a little bit more about probability distributions, because these are really central to understanding how random variables work. A probability distribution describes the probability that a random variable takes on a particular value. We write it in notation like this: the probability that X takes on a specific value, small x. We can think of this in purely mathematical terms. Random variable taking on a value. It can equally be interpreted as the probability that something happens, the probability that you roll a 2, the probability that you flip a heads, the probability that a reaction happens. And whichever is more comfortable for you to think about, feel free to use that in sort of your interpretation of what a probability is and what a probability distribution describes. There are some rules about what probability distributions have to look like that make sense when you think about them in terms of real world probabilities. First of all, the probability of any event or outcome must be non-negative. We can't have a negative probability. It doesn't make any sense. We write this by the probability that X takes on the value X has to be greater or equal to 0 for every X in the set of possibilities. Right? 0 is possible. We can have a 0 probability. It may be absolutely impossible to have a certain thing happen under certain circumstances, but greater than cannot be negative. Secondly, the sum of probabilities over all possible outcomes. If we add up all of the probabilities over all of the things that could happen, all of the possible values that a random variable can take on, it has to be 1. That is, if you think about all of the, what's the probability of rolling a number on a die? Not a specific number, but just actually getting a roll of a die. Well, if you roll it, there has to be a result, and so the total probability has to be 1. And we can write this like this: the sum over all possible values in Sx of the probability that that random variable takes on each of those values is 1. There's actually a corollary of these two results. If we have to add up to 1 and none of them can be negative, that also means that none of them can be greater than 1, because we can't add up to 1 with a number greater than 1 if we don't allow negative numbers to offset. All right. It's also worth noting that depending on the problem, we sometimes need to include the so-called null event. That is, that nothing happens in this sum. Right? Let's say we make a distinction between, so we could say, what's the probability that a coin flip gives a head or a tails? Right? There's only 2 possibilities, heads or tails. Each has a probability of half. We add them up, we get 1. If, on the other hand, somebody is sitting there flipping a coin over and over and over again, flipping it, putting it on the table, picking it up, flipping it, putting it over the table, and so on. And we ask, what's the probability that there's a heads on the table? Well, there's part of the process that we have to factor in what's the probability of there being a heads and a tail. There's also part of the probability that has to factor in what if a flip hasn't happened in that short period of time, right? What if the coin is still in the person's hand? And so depending on the circumstance, we need to sometimes take account for that, and sometimes not. And it's usually obvious in context which case we are in. I'm specifically talking about here, when we're talking about sums over possible states, so-called discrete probability distributions. These are where the set of choices are a set of well-defined numbers that we can sort of count through. Rolls of a die, flips of a coin, cards out of a deck, and so on. Not continuous numbers like any number on a number line. And we're going to talk about those slightly later. With probability distributions, we can describe them in detail with what are the probabilities for every possible choice. We also can give some general properties about them. 2 of the ones that we very commonly refer to are the expected value and the variance. The expected value of a random variable is the value we would expect to get if we took the average over a lot of independent observations. Right? So for a coin flip, if we flip a coin, or say maybe a dice roll, we roll a die over and over and over and over again, and we record the number 100 times, 1,000 times, and then we average all of those. What do we expect the average to be? Well, in that case, we expect the average to be 3.5. There's an equal number, an equal distribution of choices from 1 to 3 and 4 to 5, and the midpoint, everything's equally distributed, is 3.5. It can be computed as a sum over all of the possibilities, the value of that possibility multiplied by the probability that we actually get that probability. Right? Expected value, sometimes simply referred to as the mean or the average of the probability distribution. The variance is formally the expected value of the squared deviation from the mean. What do we mean? It's as if we take the same definition of the expected value, a sum over the value times the probability, but instead of the value, we take the value minus the mean or the expected value, and we square that. We don't really need to dig into the details of why this is defined this way. It gives us a measure of how spread out the values are. If the variance is small, it means that the distribution of probabilities is very tight. There's not a very wide range of choices. Whereas if the variance is high, it means there might be quite a large spread in the values that we see. we can also compute the variance in a slightly different way. We can also compute it as the expectation value of x squared minus the square of the expectation value. Either one is different, is equally fine. For the purposes of our class, we're not going to be digging into calculating variances, and so we don't really need to worry about it too much. But it's good to know that it's there, because it is something that does come up at times. What do some discrete probability distributions look like? Well, a very common one is the discrete uniform distribution. It has a set of choices from A to B in intervals of 1. The probability of having any of those options is simply 1 over n, where n is the number of choices. The expectation value is the average of the lowest and highest number. And the variance is actually given by the number of possible choices squared minus 1 over 12. This is the probability of a coin flip, of a dice roll, of the stereotypical pick a number between 1 and 10, if it was actually truly randomly pulled out of people's heads, or the probability distribution that underlies lottery games like Powerball. Okay. Another very common discrete probability distribution is the binomial distribution. This describes the probability that you get k positive results if you've tried n times, where p is the probability of getting 1. So for example, if you ask, what's the probability of getting 6 heads out of 10 rolls of a die, or 10 flips of a coin, the binomial distribution would get that. In that case, the underlying probability would be a half, the chance of getting heads on 1 flip. The number k positive outcomes we'd be looking for would be 6, and the number of trials would be 10. It's given by this formula here for an arbitrary k, n, and p. The expectation value is the product of how many trials and the probability of getting a positive outcome, a very simple average. Another very common probability distribution of discrete values is the so-called Poisson distribution. This is the probability of observing k events in a certain amount of time, where lambda, the key parameter to this, is the average number expected over the same time. So you might say the subway comes every 10 minutes at a particular time of day. Right? That's an average value. It doesn't come exactly every 10 minutes. It comes on average every 10 minutes. The Poisson distribution might say, what's the probability that it comes after 8 minutes? Sorry, let's back up this a little bit. Not quite the probability of seeing that it comes after 8 minutes. What's the probability that if you wait half an hour, you see 3 events, or 2 events, or 1 event? The average number in that half hour would be 3. But what's the probability that 4 trains come, that 1 train come, and so on? That is given by the Poisson distribution. We're going to find that the Poisson distribution is very central to the work we're going to get into later. Now, for some types of random variables, they take on values from a continuous set. They might be any number, and not just any number between 0 and 1, any number between 0 and 100, any number between negative infinity and infinity. Right? Continuous set. In this case, we have to use a probability density function. It also has to be non-negative everywhere. But the way we think about it has to be a little bit different, just because there's an infinite number of choices we're dealing with, and we need to kind of deal with that in a robust way. We use the rules of calculus for doing this. Right? The probability distribution function, the probability density function describes the probability that the random variable takes on a value in a tiny, tiny region around X. That is the probability that the random variable is between X and some X plus dx, where dx is an infinitesimally small value, is the probability density function times dx. To convert that to a more finite probability, this is an important result. The probability that an outcome is within some region is given by the integral of this probability density function. That is, the probability that a random variable is between A and B is the integral from A to B of this probability density function. If we integrate over all of the possible outcomes, this integral always has to be 1. This is equivalent to the fact that the sum over all probabilities has to be 1. I should note that in this integral here, whether we have a closed boundary or an open boundary, that is, if these are less than or less than equal signs, doesn't actually matter, doesn't change the result, because the inclusion of a single number out of an infinite set doesn't change the probabilities in any way. All right. We can define an expected value and a variance in very analogous ways. The expected value is an integral over the product of x and the probability density, and the variance is the integral over x minus the average squared times the probability density. All really the same things. Again, this is not stuff you need to memorize. We have it here to introduce you to the language and the notation, because we will use some of it later on. Some common continuous probability density functions include the continuous uniform distribution. We use U A to B to represent this. This is a probability distribution that looks like this. There's a 0 probability of being less than A. There's a uniform probability of it being between A and B, and a 0 probability of being greater than X. This is an even chance continuous distribution, where every possibility in the allowed interval has the same chance, characterized by the equations here. Another very commonly observed continuous distribution is the normal distribution. This is the bell curve that is often discussed. It has actually an allowed set of values that go from negative infinity to infinity, and has a shape like this. Key things about the normal distribution are that it's symmetric. It has a perfectly balanced shape around some average, and the key parameters are the average mu, that says where the peak of this distribution is, and the variance sigma squared, which describes how wide the distribution is. So this very peaked curve in the middle has a low variance. This wider distribution that has the same mean has a wider variance. This other curve here has a shifted mean. Its mean is -2 instead of 0 for the rest of them. The normal distribution is seen all over the place because it's what we actually expect as the distribution for a value that comes from the arithmetic average of a lot of different other independent random variables. So really, any random event that is governed by a whole bunch of other random events that act in kind of an additive fashion in some sense should end up giving us a normal distribution. And there's lots of such things that we can observe, and so we see normal distributions very often in practice. The last one I want to introduce is the exponential distribution, shown here. The exponential distribution has notation is shown here. X is drawn from the exponential distribution. It has a single parameter, lambda, that describes both the expectation value as 1 over lambda and the variance as 1 over lambda squared. It has the shape of an exponential decay as shown here, and the rule for this is given here, for the PDF is given here. Sorry, this extra little line here was copied from the normal distribution. So we'll just cross out that little note here. The exponential distribution is also going to turn out being important for some of what we do moving forward. All right. Let's now discuss a little bit about some properties of probabilities, how we work with them. First, remember that a random variable cannot take on more than one value in a single event. Right? When we roll a die, the outcome is well defined. It can't be multiple things. That means that for a single observation, we have mutually exclusive outcomes. When we roll the die, it's either a 1, or it's a 2, or it's a 3, or so on. When we have such mutually exclusive events, the probability of at least one of those things happening is given by the sum of all of the probabilities, right? So if we say, what's the probability that it's a 1 or a 2 or a 3? We add those probabilities up. Right? What's the probability of rolling a 2 or a 5? It's 1/6 plus 1/6, which is 1/3. We say that a set of events is independent if the outcome of one has no effect on the probability of another. When this happens, the probability of all of the events happening is the product of the probabilities of each event. So what do we mean by this? Well, the probability, say it's the probability of rolling a 2 3 times in a row. Each roll of a dice is independent. It doesn't, the result we got on the first throw doesn't affect the potential outcome of the next. And so the probability of rolling a 2 3 times is 1/6 times 1/6 times 1/6, or 1 in 200, a pretty rare event. Okay. What we've been discussing so far have mostly been what might be called univariate distributions. There's one random variable we're worrying about. Many processes involve more than one thing happening at once. Easy to visualize ones are thinking about, say, the roll not of a single die, but the roll a cup full of dice. Each of the dice has its own random variable, but we can observe multiple outcomes in a single experiment. This sort of process are described by more than one variable, more than one random variable, and there's a number of different probabilities we can define to describe this multivariate set. A joint probability is the probability of a specific simultaneous lit set. Right? So if we had two variables, x and y, the joint probability is that x takes on one specific value and y takes on another specific value. Both things happen. The conditional probability is the probability of one thing happening when we know something about the others. We write this, the probability of x given y. And what this means is, what's the probability that x takes on a certain value if we knew that another value was taken on, right? So let's say, for example, there can be a distinction here. What's the probability if you draw two cards from a deck, right? What's the probability that one is a 10 and one is a 4, right? You can, that would be the joint probability. What's the probability that one is a 10 given that the other is a 4? Well, here that matters, right? Because the fact that you know that one is a 4 means that the remaining set is slightly less, right? You only have 51 other choices instead of 52 other choices, a little bit of a different number than just the probability of drawing a 10 from an original deck. The marginal probability is the probability of a particular event, generally ignoring the effect of other variables. We simply call this, say, the probability of x, the probability that x takes on a certain value, and it's actually given as a sum or an integral, depending on whether we have discrete or continuous variables, over all of the joint probabilities that involve that particular variable. We're not going to be digging a lot into multivariate distributions, but since we're giving a review of probability, I wanted to include it. Conditional probabilities can be related to the joint and marginal probabilities as a well-defined relationship. The probability of x given y is the ratio of the joint probability of x and y and the probability of y. These are usually order dependent. That is, the probability of x given y is not equal to the probability of y given x. This definition should make it clear why. Joint probabilities, the order doesn't matter how we write it because both things have to be true. But the probability of x given y would have a denominator of y. The probability of y giving x would have a denominator of the marginal probability of x. Unless those happen to be the same, we'll get a different value. We can reverse the order using something known as Bayes' theorem. It's actually fairly straightforward to derive. The probability of y given x is the probability of x given y multiplied by the probability of y divided by the probability of x. This just accounts for the fact that we change the denominator in changing the order, and this does this, right? Finally, we talk about independence of random variables. Two events or two random variables are considered independent if their conditional probabilities are exactly the same as their marginal probabilities. That is, the choice of the second variable doesn't affect the probabilities. They are independent from one another, right? So the probability of x given y is equal to the probability of x. The the probability of y given x is equal to the probability of y, and this has to be true for all possible choices of x and all possible choices of y. When we have independent variables, then the joint probability is given simply as the product of the independent marginal probabilities. As we actually discussed before, independent events multiply their probabilities. All right, so that wraps up our brief intro to the language of probability. Random events can be described mathematically with the concept of a random variable, a numerical representation of such an event. We don't usually make a distinction between truly random events and events that are effectively random. We treat them the same way when we work with them mathematically. The properties of a random event are characterized by probability distributions or probability distribution functions, probability density functions, depending on discrete or continuous variables. And many of these have been extensively studied and well characterized, and we can take advantage of the fact that we know lots about those distributions to use them in solving interesting problems. All right, so with that, we'll end this probability primer, and in the next video, we're going to start using these ideas to really build up our modeling framework for looking at biochemical reactions with this stochastic random nature of the underlying reactions taken into account. Until next time, take care and be well.